Let's explore some examples of NP-complete problems. These are classical problems in computer science that are known to be among the hardest problems in the complexity class NP. We will introduce the concepts with the examples in subsequent slides. Here we will introduce the SAT problem, or Boolean Satisfiability problem, which involves determining if there exists an assignment of truth values to variables that makes a Boolean formula true. We also discuss the Hamiltonian Path problem. This is a graph traversal problem. In this problem, we want to find a path in a graph that visits each vertex exactly once. Let's delve into the SAT problem, also known as the Boolean Satisfiability problem. The definition of the problem is as follows. Given a Boolean formula, can we determine if there exists an assignment of truth values to variables that makes the formula true? In other words, can we find a set of true or false values for the variables in the formula so that the entire formula evaluates to true? Here is an example formula. Open parenthesis x1 or not x2 or x3 close parenthesis and open parenthesis not x1 or x2 close parenthesis and open parenthesis x2 or not x3 close parenthesis. This formula contains three variables x1, x2, and x3 along with logical operators such as or, represented by the symbol looking like an upside-down V, not, represented by the symbol looking like, and represented by the symbol looking like an upward V. Now let's focus on the 3 SAT problem, which is a special case of the SAT problem. The key constraint in 3 SAT is that each clause must contain exactly 3 literals connected by or operators. A literal is either a variable or its negation. For example, consider the following 3 SAT formula. Open parenthesis x1 or not x2 or x3 close parenthesis and open parenthesis not x1 or x2 or not x4 close parenthesis and open parenthesis x2 or x3 or x4 close parenthesis. In this formula, each clause, which is a group of literals within parentheses, contains exactly 3 literals combined with or operators. The goal is to determine whether there exists an assignment of truth values to the variables x1, x2, x3, and x4 that satisfies the entire formula, making it true. The Hamiltonian Path problem is a classic graph traversal problem. The definition of the problem. Can we find a path in a graph that visits each vertex or node exactly once? This means we're looking for a route through the graph that starts at one vertex, visits every other vertex without repeating any, and ends at a different vertex. Consider a simple graph with vertices labeled A, B, C, D, and E. A Hamiltonian path in this graph would be the sequence A to B to C to D to E, where each vertex is visited exactly once. The challenge is to find such a path in a given graph, or determine that no such path exists. Now let's delve into the vertex cover problem. Given a graph, the problem is to select a subset of vertices such that every edge in the graph has at least one endpoint in the selected subset. In other words, we want to choose a set of vertices that covers all the edges in the graph. The objective of the vertex cover problem is to find the minimum vertex cover. This means we want to cover all the edges using the fewest vertices possible. This constraint ensures that we are finding the most efficient vertex cover, minimizing the number of vertices needed to cover all edges in the graph. Next, let's explore the Clique problem. The definition of the problem is as follows. Given a graph, can we find a subset of vertices where every pair of vertices in the subset is connected by an edge? In simpler terms, can we find a group of vertices within the graph such that there is an edge between every pair of vertices in the group? The Clique problem has a key property. A clique forms a complete subgraph within the original graph. This means that all vertices within the clique are mutually adjacent. There is a direct edge connecting each vertex to every other vertex in the clique. The Traveling Salesman Problem, or TSP, is a classic optimization problem. The goal is to find the shortest possible route that visits each city exactly once and returns to the starting point. Imagine you're a salesman who needs to visit several cities and wants to minimize the total distance traveled. The traveling salesman problem has one major constraint. The solution must form a Hamiltonian cycle. the salesman must return to the origin with the minimum total distance traveled. The Hamiltonian cycle ensures that every city is visited exactly once, and the return to the origin completes the cycle. Let's discuss the key characteristics of NP-complete problems. One of the key properties of NP-complete problems is that all NP-complete problems are polynomial time reducible to each other. This means that if you have a polynomial time algorithm to solve one NP-complete problem, you can transform any other NP-complete problem into an instance of that problem and solve it in polynomial time as well. The major implication of this property is that if you can solve one NP-complete problem efficiently, then you can solve all problems in the complexity class NP efficiently. This would have significant implications for computer science, as it would mean that many currently intractable problems could be solved quickly. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.